Good morning, everyone, and welcome to the best paper session for the first session. I'm Dr. Jade King. I'm from the AFRL 711th Human Performance Wing, and I'll be the chair of this session. We also have our deputy chair, Duke Tucker, and he's from Pinnacle Solutions, and we thank you for attending our paper session this morning. We will be hearing from 3 papers during this session, but first, I need to review a few items. As a courtesy to our presenters, please silence your mobile devices. Also, each paper will have 20 minutes for the presentation, followed by 5 minutes for Q&A. And so we will stop at exactly 25 minutes to give the next presenter time to set up. Please no flash photography or video recording, and be sure to obtain your CEU credits if you're interested. Our first paper is Building a World with Deepfake Content, Who Needs Real Data? Presented by Mr. Long, who has 33 years of experience in the simulation industry, working with visual systems and synthetic environments, and currently works for Tails. Ladies and gentlemen, it is my pleasure to present Mr. Long.
Thank you, and good morning. So, building a world with deepfake content, who needs real data? So I'd like to begin by introducing you to this group of people that share a common secret. And that secret is that none of these people are real, none of them exist. Every one of these is a deepfake image generated by an AI model. And these are probably the most relatable example of the power of this technology to create totally fake, but very plausible data that's so realistic, it's indistinguishable from real data. And these highlight both the potential of this technology, but also underline the necessary caution and concern it raises around potential misuse and issues of data ethics and security and trustworthiness. Now, the term deepfake reflects the fact that this fake data is being generated by deep learning neural networks. And the term deepfake is synonymous with the creation of fake images and videos of people. And although it's a very catchy term, in actual fact, deepfakes belong to a class of machine learning models known as generative models. And these possess the amazing capability to learn the patterns and structures and distribution of real data, to learn a model of how that data was generated, and then apply that model to create synthetic or fake versions of that real data. And generative modeling is a rapidly emerging field of AI. It's being applied to many domains and many problem spaces. And the question for me was, how could this be applied in the context of synthetic environments? So a little bit more about generative modeling, first of all. So in order to create fake data, generative models need to understand something about the distribution of the real data. So if a model was to be trained to generate fake images of cars, it would be provided with a training data set of real images of cars. But it cannot learn the true distribution of that data just from the training data set. But it can learn a very good approximation of that data distribution. And once it's done that, it can sample from that distribution to generate fake data that appears to belong to that original data set. But in practice, these data distributions, they are very complex, they're very difficult to learn, particularly for high-dimensional data like imagery. And this is where the properties of neural networks come into play, because neural networks are very good at learning these complex functional mappings and data distributions. They're also very good at learning the underlying patterns and structures of data. So a neural network can receive a set of images as input, and during the training and learning process, it can learn the unobservable, hidden, or what's referred to as latent features or variables of that data. And these are the subtle characteristics and nuances of the data that provide the model with some data understanding. And these latent variables are encoded in the neural network in an abstract place referred to as a latent space. And it's this combination of learning these latent variables and that data distribution that provide the model with the ability to generate fake data. So there's a whole family of deep generative models, but I'm only going to focus on one today, which is the Generative Adversarial Network, or GAN. So these approach this data learning problem by adopting an adversarial game theory approach to learning and using 2 neural networks in competition with each other. So there is a generator network, and its job is to learn how to create realistic fake data, and a discriminator network whose job is to identify real from fake data, and it's trained with some real data. So the training process begins by feeding some random noise to the generator. It attempts to generate some realistic fake data. That gets passed to the discriminator. It tries to determine, is that real or is it fake? If it believes it's fake, it provides some feedback to the generator model via a backpropagation process. The generator adjusts its internal weights and has another go at trying to generate some fake data. And the goal of the training process is to iteratively repeat this cycle so that the generator progressively becomes better and better at creating fake data until it reaches the point that it's so good the discriminator can now no longer identify it as fake. And at that point, we've got a trained model. So GANs have made some tremendous progress since their introduction in 2014 when they were generating the low-resolution grayscale images we see on the left, and they've now improved to be producing very highly realistic, full-color, 4K, high-resolution images that they are today. And GANs certainly excel at computer vision tasks and these image synthesis tasks, but they're also now being applied to a wide range of other applications as well, and this ranges from drug discovery, predicting stock market trends, and even generating software code. And they're also now being widely applied to the generation of synthetic data to train other AI models, because one of the big challenges in machine learning is building training data sets of real data. It's a very significant activity, and very often those training data sets can be susceptible to problems like bias. So the ability to generate high-quality synthetic data that can be added to those training data sets has got a lot of benefits. So the question for me was, how could all of this be applied to synthetic environments? But perhaps the first question is, why even bother at all? Because there's now an abundance of very good real data that's available to us. There are many platforms capturing many different data types, generally at a high tempo, high velocity, high volume, and generally the quality of that data is also improving. So all of that is true, but real data also has problems associated with it as well. And when building a synthetic environment, very often the first problem is where to obtain the data that we need to construct that environment. There may be issues over data affordability, availability, access. It may not be available at the right sort of quality or resolution. It may be incomplete. So the ability to generate synthetic data gives us some benefits. We can augment, supplement, or replace real data. It also opens up new opportunities because we can now begin to generate data on demand at scale, independently of the collection of real data. It also opens other possibilities where we can look at things like what-if scenarios, because real data is a snapshot of the world at the point that that data was captured. But if we wanted to explore what would this data look like under different conditions or different scenarios, we could actually explore that and generate those variations with synthetic data. So what I'm going to do now is just show a few limited examples of some of the synthetic environment data types that we could create using these generative techniques to generate some fake versions of that data. And I'm going to begin with synthetic imagery generation, and specifically the generation of fake satellite or aerial data. And this is going to use a technique called image-to-image translation. So this can translate an image from one domain, which in this case is going to be a real Google map tile, to another domain, which is going to be our fake satellite image. But this presents the first problem, because although GANs are very good at generating fake images, in the example of faces, it is the GANs themselves that are randomly deciding what the composition of those faces will be. So it's deciding if the person will have blonde hair, black hair, what gender will they be wearing glasses. But that's not particularly useful if the goal is to generate fake data that represents the real world. So we need to have some control over that output, and that can be achieved by using a conditional GAN. So a conditional GAN conditions the fake data on another piece of real data, which in this case is our Google map tile. So that can be fed to the generator model, and the generator tries to create a fake satellite image that reflects that Google map tile. And in this case, the discriminator compares that to real pairs of real images and real map tiles. And then the model goes through the same training cycle that I described earlier until the generator is creating the fake images that we see on the right-hand side. So this image reflects that Google map tile. It contains all of the features, and they're configured and geolocated as they are in the map tile. But the visual appearance of that image has been learned during the training process from the training data set. So in this way, we can actually generate a real ground truth. We're creating a fake image, but it represents a real area of the world. But as I mentioned earlier, we may want to explore something like a modified ground truth and see what if scenarios we can play. So again, we can use a technique called image-to-image translation. But in this case, something slightly different, something called style transfer, and a slightly different GAN architecture called a cycle GAN. So in this case, again, the input is a real map tile. But in this case, rather than generating a fake image that has the visual appearance that reflects the area of the world covered by the map tile, we could generate a fake image that contains all the features from the map tile, but whose visual appearance has been transferred from somewhere else. So in this case, the first image is the map tile on the left, which is from Tacoma in Washington State, and we generate a fake image that represents the visual style of Seattle. So visually, it's not very different from Tacoma because geographically they're not very far apart, but we could do something more radical like generate that map tile with the visual style and appearance of Beijing. And in theory, we could generate that image with any style from any location on the Earth, or perhaps something much more abstract if we wanted to. So this is one way that we could generate a modified ground truth. Another is to use something like OpenStreetMap data, which is the second example, and in this case, use the semantic class data to modify the fake image that we create. So the real ground truth is on the left-hand side, and then if we increase the influence of the grass land class, then we can see that in the right-hand image there that all of the land in between the buildings, including the roads, is now been covered with grass. And if we do the same thing with the forest land class, we get a similar result, but that area is now covered in trees. So both of these are examples of how we could approach generating modified ground truths in different ways. And the important point here is there are many ways this could be done with different GAN architectures and different combinations of conditioning data. Another example is using image-to-image translation to generate some fake building footprint data. And this can use real road networks from OpenStreetMap and learn to create fake building footprints that represent the urban patterns and morphology of any location that the model's been trained to generate. So that could be London, Jakarta, Orlando. So the footprints don't reflect the precise location of the buildings, but they are a remarkably good fit in terms of the urban pattern and form. And the final example is using image-to-image translation to improve the resolution of a real piece of data. So in this case, the model can learn from a low-resolution piece of real data what the missing high-frequency component is from that data and generate a fake high-resolution version of it. So in this case, we see a low resolution on the left, that's the real data, and the high-resolution fake version of that image on the right-hand side. So those are just some examples of how we could possibly generate fake data. But once we've actually got a trained model, it opens up other possibilities as well as to how we can create fake data. And a concept that's emerged recently is that of generative data. So we can think of generative data as a combination of the synthetic data, the generative process that created it, and those latent variables that I referred to earlier. So for a model that is trained to generate fake satellite data, it will have some latent variables that are associated with the urban features in that imagery, some with agriculture, some with forestry and vegetation. And these latent variables are clumped together in this abstract place known as a latent space. So there'll be groups of urban features and groups of vegetation features. And if we can identify where they are in this latent space, we can then interpolate between them and generate all of these other intermediate images. And that's what we see in the matrix here, that we begin, in this case, we're going to interpolate on the left-hand side from forest and vegetation toward urban features on the right-hand side. And this provides a way that we can generate all of these intermediate images that have got different combinations of those features in them. And this is being done just by exploiting and manipulating what that model has learned during the training process about the data. So it's not being retrained, it's not being provided with any new data. And so in this way, generative data can really be considered different to regular data and behave differently to regular data. Another new concept that's emerged recently is neural rendering. So neural rendering combines generative modeling with the physical knowledge from a traditional computer graphics pipeline. So the flow that we see at the top here with the two boxes represents our conventional computer graphics pipeline. And there are essentially two phases, one where we generate a 3D scene representation, and the second where that gets passed to a renderer, and that could be a game engine like Unreal or a traditional simulation image generator. It then renders the 2D image as output from that 3D scene representation. But a neural rendering pipeline almost works in reverse. It can receive a set of 2D images as input, learn for itself what that 3D scene representation is, and then we can incorporate rendering capability into the network, and it can then render that final 2D image as output, which is equivalent to the conventional pipeline. But the important point here is in a conventional pipeline, that 3D scene representation is effectively our synthetic environment, and we spend a lot of time and effort creating that from polygons and meshes and textures and materials. But with the neural pipeline, we've got the potential now to learn that representation from some input data just using the network. And we can do that as a 2D rendering, which is analogous to the fake images I've described so far, or a 3D neural rendering where we can learn and render a complete 3D scene. And one example of how this can be achieved is using something called neural radiance fields, or NURBS. So these can take a set of partial 2D images and learn how to render and construct a 3D scene from that. And until recently, these have only been able to do this for single objects, but they've now advanced to be able to do this for something up to the size of a city environment, for example. And this is an example using New York City. So the input is a set of images, which is a combination of some aerial images and some ground-based images. They get passed to the neural network. It fires some rays through those images, and where it intersects features, it captures the position and direction of those rays, outputs that as color and density. And then the neural network can perform something referred to as volumetric rendering and actually render that 3D scene, which is the two example images that we see here. And as you would expect, you can navigate and fly and move the eye point through that 3D scene. So this is a very different way of generating environments and rendering them from the conventional pipeline. But this is a very immature technology at the moment. It's not going to replace a conventional computer graphics pipeline tomorrow, but probably the most likely scenario is there will be some kind of hybrid approach where we combine neural rendering and a conventional pipeline. And this is one example of how that could be done. So this is a hybrid approach where the goal here was to combine the output from a traditional game engine with a neural renderer in order to generate a more photorealistic output. So in this case, the video game is Grand Theft Auto 5, and the imagery is very good high quality, but as we can see, it's very stylized. If we look at the road surface, lots of contrast, lots of detail. So the goal is frame by frame to pass that output through our neural renderer, which has been trained on real street scene data, and then re-render that with a more photorealistic output, which is what we can see in the bottom right. So we can see here that that road surface has now been re-rendered with a more natural, smooth asphalt appearance, and the cars have got a more natural glossy and reflection appearance as well. So in this way, we can combine a conventional and a neural renderer, apply a neural renderer as a post-process, and actually change the look and feel of that scene without any access to it or without needing to perform any editing on it. So I think this has illustrated that generative modeling now has got the capability to create fake but very plausible data that we could employ in synthetic environments. And this has just been a very, very limited example of the types of data that could be used. There are many others that we could apply this to. And importantly, we can achieve the right level of control over that fake data to create something that's realistic and that we can use to generate a real ground truth or a modified ground truth if we want to. It does have to be noted that the design and training of generative models is not a trivial activity, and GANs in particular, they are known to be susceptible to some problems in the training process, although there's a lot of work and research going on to look at GAN architectures to see how those problems can be mitigated. But despite that, we've seen a lot of advancements in model architecture, model performance, and the quality of synthetic data, and a growing application of this across many domains. But within the field of AI, the future of AI is widely regarded as being generative because it's beginning to approach the holy grail of providing some understanding of the world and data to an AI model. And it's changing our concepts of data, content, and data, our creative process. It's made very little penetration into modeling and simulation and synthetic environments so far, but I believe it's got huge potential to transform the way that we think about data, the way that we construct and develop synthetic environments, and perhaps even the way that we represent synthetic environments. And I really don't think it's a question of if, I think it's a question of when we begin to see generative AI being applied, implemented, and deployed within modeling and simulation and synthetic environments. So thank you very much for your time. Thank you. Yep.
The hybrid rendering process, is that kind of what NVIDIA is doing with DLSS?
I'm sorry, I didn't quite catch that.
Is the hybrid rendering method, is that kind of what NVIDIA is doing right now with their DLSS 3.0?
Yeah, similar, I believe. So they're looking at things like real-time super resolution, for example, so that they're applying that at real time to improve the resolution of images. So I think it's a slightly different approach to this. This was actually using a completely separate renderer, and this particular example was developed by Intel as a demonstration of the capability to do this, yeah.
Thank you.
On the generative stuff, so not to oversimplify, but this is interpolation, extrapolation of the data. The AI is not using biological or physical processes to maybe capture the evolution or the emergence of some of that vegetation, for instance, right? So those images are static.
That's right, yeah. It's just learning from whatever data it was provided from in that process, yeah.
Thank you.
Hi, Graham. Nice talk for sure. So we're seeing a lot of interest in GAN-based synthetic data for training AI. We work with conventional pipelines, as you call them. One of the advantages of the conventional pipeline is you know exactly what's happening to pixel in the output imagery.
Mm.
Can you speak to any progress there around GAN-based data and knowing actually what's in each pixel in an output data set?
Well, yes, I think that's a very difficult issue because clearly the thing that nobody actually knows and has any particular control of is what's going on inside that neural network. So, yeah, being able to know with some sort of deterministic control as to what's happening with each pixel within a GAN-generated image is not, I don't think that's really possible to do that at the moment.
Thank you.
All right, so in the war on hearts and minds and kind of like historical aspects, like what we experienced like with Germany in World War II and such, how do you define or how do you actually capture what is real and what is not real? Let's say you got a country like, Germany, maybe they bomb something in Ukraine and they generate fake images and they display it as not real, right? They put, oh, we never did that. Look, here's pictures of it today. China and some other country, right? So how do we identify what is real, what's not being real, that's being actually publicized on either social media or on the actual news?
So I think for us as humans, it's very, very difficult, if not impossible. But there is a lot of research in place to develop methods that can analyze imagery and actually identify if it has been generated using these techniques. And there are methods that can do that, but it needs some analysis. So for us as humans, I think it's virtually impossible. I think if you looked at those fake images and you stared at them all day, you would never be able to tell if they're fake or if they're real. So you need analysis to be able to do that. And there are techniques being developed to enable that to happen.
Do you foresee any of that actually being public use?
I think you could imagine it going that way, yeah, because I think perhaps if this technology becomes more available as consumer products, then perhaps, yes, people would need to feel that reassurance that they can assess some of that for themselves, possibly.
How long does it take to generate an image?
When the model's actually running, do you mean? Or do you mean the training process? Or?
So both, like how long does the training process take, and then once that's complete, how long does it take to generate an image?
So the training process, it's hard to say how long it can take, because one of the issues with generating images, for example, is the assessment of when you've achieved an appropriate level of training is rather qualitative. So you may need to determine how many iterations of the training process you want to run before you reach that point. But the example I provided at first there with that first fake image, I think that had a training data set of about 1,000 images, and I think by the time it had gone through about 50 training cycles, it was producing acceptable imagery. So that's the actual training process. But then once the model is trained, the process of generating the image is extremely quick. It's not a long process at all. It's just a matter of seconds to go and generate those images.
So the faces was about 1,000 images?
No, sorry. The first example of that fake satellite image,
Yeah.
that was about 1,000 images in the training data set. I think it went through about 50 training cycles, 50 to 100, I think, depending on what your determination is of how acceptable the image is that it's creating.
And that takes a few minutes to go through it?
No, the training cycle, that's going to be very dependent on the hardware that you train on, and the size of the data set. So you could be looking at many hours to train a model.
Okay. And then just a few seconds to generate an image?
Yeah, once the model's trained, yeah.
How many images were in the study to create the faces?
I don't know. So those faces are actually taken from a website called isthispersonreal.com. So you can just go to that web page, just keep on hitting return, and it will create your faces for as long as you want to sit there and watch.
How would you generate a pseudo-random change in the scene, such as, say, snow melting or vegetation growth or corrosion over time?
That would need to be a combination of training data that can educate the model as to what those effects are. And there are models that do that now, so or something similar. So there's a model called DisasterGAN, for example, and it's been trained to generate images of real areas of the world to reflect the impact of different natural disasters. So you could see what the impact of a flood or a fire or an earthquake. So, but to do that, you need examples of those effects to train the model to do that. But there are many examples of using this to give different appearance of seasons or snow cover, or to adapt the image really in whichever way you see necessary.
Something like a fractal algorithm?
I'm sorry, I didn't hear that.
I'm asking whether using fractals, would that help in that particular representation?
No, this doesn't use those techniques. So you would need to have some example data of the effects that you're trying to create and incorporate those into the training data set. That would be the way that it would work. One more, sorry.
Has this method been used for generating fake data for other than imagery, for example, traffic patterns or even Twitter feeds, who knows what else?
Yeah.
Things other than imagery.
Yeah, it's generating all sorts. Art, it's generating blogs, text, prose, music.
Thank you so much.
Thank you.
Yep, I think so. Thank you. Yeah, just be standing here is fine.
So should we assume this is live?
Should be. Yes, it is.
It looks live.
Yes, it is. Hello, everyone. Welcome to the Best Paper Session 1. Our second paper is Semantic Fidelity Reckoning Toward Normalized Simulation Interoperability in Digital Engineering. Dr. Rick Roca and Mr. Daniel Winton come to us from the Aerospace Corporation. Rick has over 35 years of experience and holds a PhD in modeling and simulation engineering. Daniel is a practicing digital engineer and has 32 years of experience and holds a master's degree in system management and system architecture and engineering. Ladies and gentlemen, please welcome Dr. Rick Roca and Mr. Daniel Winton.
Let me get this real quick here. Set up here. Set up here so we can go. Start. Okay, good morning. I am Rick Roca.
I'm Daniel Winton.
Thank you for attending our session today. A lot of ground to cover here, so we're going to get right to it. Let me see if I can first get my slide up here. I didn't notice.
Here, there should be like the slide.
This one?
Nope, not that one. Where's the cursor? I can't find it at all. It's that one right there.
Okay, we got to do that. I can't. Yeah, it's not working. So we can't get it to work. So
We're trying to get the slide. Trying to go into slide mode.
thank you.
We will absolutely look forward to it.
Sorry, 1 second. Okay.
Technical difficulties. We'll be right with you. Is that
Here
it?
we go.
All right, let me stop again. We don't get penalized for that, right? All right, again, good morning. Thank you for our session. Again, I'm Rick Roca. This is Daniel Winton. Let's see. So, where is the? Okay. So the Office of the Secretary of Defense for Research and Engineering issued a not so flattering report card last year. It focused on simulation interoperability deficiencies. We lack standards and tools for integrating modeling and simulation as part of digital engineering. We also provide insufficient guidance for implementing interoperability across the military services and other domains so that their models can exchange data meaningfully. Okay. Daniel and I work at a federally funded research and development center, and last year we worked on a feasibility study to address specifically these digital engineering simulation deficiencies. Daniel, he is a lead. We met at the Verification Sciences and Engineering workshop where he is the digital engineering lead. So Daniel, what are your observations on model-based systems engineering realm, and are they consistent with his report card?
Yes, I agree. There are issues with our model-based systems engineering solutions because they're based on a paradigm called SysML, which allows you a lot of flexibility in building your models, but that also means that you end up with different ontologies, and those ontologies make it difficult to share information.
Thank you, Daniel. Okay, our study examined three paradigms: semantic fidelity, which aims to normalize the Fidelity specification of modeling and simulation analytic models, semantic fidelity reckoning, which aims to reconcile disparate fidelities among analytic models, and then the constraint block handshake, which aims to implement or leverage semantic fidelity so that analytic models and the MBSE descriptive models can talk to each other effectively. Okay, so we're talking about digital engineering, interoperability, domains, standards, a lot of stuff that, problem that, with a bunch of interrelated complexities. So let's address here digital engineering and interoperability. There are different levels of interoperability. I'm going to talk only about two of them because in the interest of time. Syntactic interoperability refers to the exchange of data in agreed upon formats. This has been largely conquered. Semantic interoperability, on the other hand, is the exchange of information. This is data in context, or more specifically, the exchange of data in agreed upon contexts. This remains elusive and a problem. Now, let's look at digital engineering. The definitions from the literature tell us that it is a continuum of models from different domains with an enabling infrastructure for the exchange of data. Well, this multi-domain environment implies the need for semantic interoperability, okay? Now, we're gonna take a look at just a couple of these domains. You have different kinds of domains: scientific, engineering, economic, acquisition, human factors, etc. So we're gonna look at only two of them. The model-based, the analytic models for simulation systems and the MBSE descriptive models. Okay, the M&S analytic models, these are your phenomena representations, dynamics, physics, those kinds of things. And their essence comes from fidelity specifications. So if you have inconsistent or arbitrary fidelity specifications, that's going to be manifested in computational errors that propagate across the distributed simulation environment, and they will propagate into the digital engineering ecosystem. Excuse me. The MBSE descriptive models, these are your structure and behavior diagrams for specifying operational systems. These are your SysMLs, your those kinds of models. They use ontologies. And also, if you use arbitrary or inconsistent ontologies, you're going to have as much a problem with communicating, propagating computational errors as much as not being able to interoperate at all, okay? So, excuse me. Now, the analytic models and the descriptive models are meant to work together iteratively. We use parameters are included in the descriptive models to constrain the design of specifications of system designs. Those parameters usually come from reference, from authoritative sources, from subject matter expertise. But as we face emerging threats, emerging challenges, and we aim to maintain a tactical and strategic advantages, we venture into uncharted territory sometimes, where we don't have the full knowledge, the full body of knowledge available to us. And that's why we need analytic models, the simulators, so they help us fill in those knowledge gaps. Now, last point on this. One descriptive model may use multiple analytic models, and one analytic model may support various descriptive models. So when you have arbitrary or inconsistent fidelity specifications and inconsistent ontologies or arbitrary ontologies, you have an exponential semantic, the semantic disparities become exponential. And here we're talking about only two types of models. So when you have the entire digital engineering ecosystem, that's what's getting very, very complex. Oops. So we're going to push forward, but first we're going to have an audience participation challenge brought to you by some of my software engineering friends. So, and this is to make a point, okay? So here we go. How many software engineers or programmers does it take to screw in the light bulb? Anyone? Daniel?
No, I have no idea.
All right. It can't be done. It's a hardware problem. So, but there's some truth to this, okay? Here's the takeaways. Models are not software-centric. They're not hardware-centric, and they're not tool-centric. In fact, they're agnostic to those three. Models are domain-centric, which means that we have domain differentiation matters, and cross-domain collaboration is imperative. That point right there is in fact captured in formalisms. Software engineering, there's a software engineering postulate that tells us that software designs, domain software designs, are constrained by domain premises. And the corollary to that is that Fidelity specifications provide the baseline for model validation. So domains are important. We have to pay attention because domains give us important information about the accuracy of models, but they're also, when you start mixing different domains, you start having semantic disparities, and we've got to be very conscious of that. The ontology research community tells us that people perceive problems differently, they model them differently, and they express those models differently. So, that leads to the kinds of ontology disparities that Daniel was alluding to earlier. Excuse me. The semantic disparities also include other things like general misconceptions or concepts and terms that are overloaded or interchanged. This little box in the middle there shows you just a little example of resolution where you use different resolutions and you arrive at the same answer. And that's just a really tiny example of some of the problems we can face if we don't pay attention to these things. Okay. Now, if those semantic disparities are susceptible to generic taxonomies, because generic taxonomies allow you to really arrange things any which way you want to. Here's a very simple example of geometric figures to represent a problem space and how you can arrange that differently. Well, when you combine that or you couple that with a lack of fidelity specification standards, okay, now that leads to having distributed simulation environments where you have arbitrary fidelity specifications, which then it's a hodgepodge of fidelity there. So you have you end up with a lack of semantic interoperability. You're going to be propagating a lot of errors. Okay. We need an alternative to that, something that allows us to have consistent fidelity specifications. Now, there's a good reason to have different kinds of fidelity, but we want to either have consistent fidelity or a mechanism that allows us to reconcile different levels of fidelity. Okay, so we want to have an apples to apples situation. If the other one was just apples to oranges, we want to have an apples to apples or an apples to oranges that is reconcilable. Semantic fidelity, the backbone of semantic fidelity is something called a phylogenetic taxonomy, and I'm going to speak to that in the next slide here. So just to recap, generic taxonomies are arbitrary. You can, it leads to ambiguity, whereas phylogenetic taxonomy, they're not interchangeable. A phylogenetic taxonomy is a taxonomy of phylogenies. A phylogeny is basically a very specific to a particular species-like. And using them mitigates this ambiguity that we're talking about across domains. Okay, so what's a phylogeny? Let's first clarify. A taxonomy is a classification of things. An ontology is a specification of a thing. Usually you want to have an ontology within a taxonomy, like a fox belongs to the taxonomy of zoology. And so the difference is a phylogeny is the historical development or the emergence or evolution of a thing, how it comes to be. So, for example, for an organism, you have DNA as a building block. DNA gives you cell, you go to cells, and then cells to tissue, tissue to organs, organs to systems, and you end up with the organism at the end, okay? Well, semantic fidelity aims to follow a similar reasoning, where you look at a problem space or a phenomenon through a prism of computable entities and entity relationships as those building blocks. Those building blocks become what I call computable model DNA, and you can construct phylogenies from that. So a phylogeny is a specific configuration of a model, and so I call that a computable model species. So you can construct a phylogenetic taxonomy of different kinds of computable models, and those models should fit in there. If you want to have a different kinds of a variation, like a blue fox and a red fox, you just have a different phylogeny. You just have different components included in there. Okay, this is the decomposition of that prism, where you have dimensionality, which refers to dimensions, like length, time. This comes from dimensional analysis. You can specify the types of phenomena, the types of variables, constants, parameters, and so on. Metrology, which is the science of measurement, and then numeracy, which is like literacy, but with numbers, where different kinds of mathematical methods that you can use to express the model. Now, one of the big advantages of this approach is that you can have nomenclature that captures those phylogenies, if you will. Okay? So as you can see in this example here, if you have a projectile motion, you can have simple projectile motion. You can have any number of perturbations, and those will be reflected in perhaps a numerical, in a bit mask nomenclature strategy. Such a strategy would be it could provide an identifier, like ISBN codes or QR codes do it for books and other things. Okay, so
And that saves lots of time and money because you don't have to reinvent the wheel on a regular basis.
Yep, that consistency is good like that. So it's a better alternative to low, medium, high fidelity that's completely uninformative. Now, if in addition to being able to catalog and discover and validate models in that way, it gives you a good foundation for an enumeration mechanism for semantic interoperability, similarly to what DIS does, the distributed interactive simulation. Okay, so those of you who are not familiar with DIS, it's a IEEE standard for interoperability. DIS has a mechanism called dead reckoning, so that instead of transmitting locations constantly, X, Y's, and Z's, you just send an equation of that trajectory as long as it's constant, and that way you can compute that position locally and not have that traffic. That's important when you're dealing with a digital engineering ecosystem that's got many things communicating. Well, semantic fidelity reckoning extends that idea so you can transmit an entire fidelity specification across the wire, and you can compute those locally. Okay, we did our study included, we stood up a couple of rudimentary simulators, one for a satellite to compute its orbit, one for an anti-satellite missile to compute the trajectory. The context was the satellite was going to intercept the satellite. The missile was going to intercept the satellite. Excuse me. So the LEO sim computes the orbit and sends that information to the other simulator. It picks up those data points, and then it predicts, it fits those into an ellipsis to predict where it's going to be in the future, so it can compute its trajectory so it can intercept it. That's fine. But when you change the fidelity and you include something like drag, which causes a decaying orbit like a spiral, then when the other simulator with the ECIT sim tries to fit an ellipsis to that, you're going to end up with errors. So you're not going to have an effective interception. Well, what we did is we then implemented the semantic fidelity reckoning so we can communicate how much fidelity, which types of fidelity we were having, and that worked perfectly well. It was very effective no matter what trajectory or what kind of orbit you were computing. I'm sorry, Danny?
That's good. So, here you go. We took what Rick has put together and we built it into a non-systems markup language, model-based systems engineering environment. And what we ended up with was something where we could share all of the information about a particular semantic fidelity situation. And so this is kind of a quick look at it. We included all of these other things. I won't read them off to you. And this is what it looks like in the model. we have not only brought over the information that came from the simulator, but we've tied it to not only the design, but in addition to the requirements and the cost and the schedule, because we're sharing the parametrics all across the environment in a digital engineering solution. This is a very small part of something I call the common information infrastructure, which is predefined element types and relationships between those element types so that we can have a complete digital engineering picture in the same model. And so here you go, we got a couple minutes.
So the path forward for us here, which really it's a work in progress actually, is to be able to capture or phylogenetic taxonomy in MBSE constructs like use cases or other mechanisms like that, so as to make it a selectable. It's a repository of selectable, reusable modeling primitives. That way, systems engineers don't have to be subject matter experts. They can pull those kinds of perturbations, for instance, whatever you want to add in your design, you can capture those and put them in your descriptive models. Those descriptive models in turn inform or provide the specifications for the analytic models for simulators. They can crunch the numbers, send back optimized parameters, which can then be sent to or made available to the operational system design engineers. Yes, that's.
Here's a picture of our study. We had a launch vehicle, and we said, hey, we want to be able to make that launch vehicle shoot down a satellite. So we're going to launch the thing in our simulator. We have the simulators go up, and guess what? That launch vehicle did not actually hit that satellite. But wait, the two simulators have differing semantic definitions. So what are we going to do? Let's apply semantic fidelity. And then we're going to launch the vehicle again, and boom! Modeling and simulation semantic fidelity changes everything.
The other simulators were a lot more detailed than that one, but
Yeah.
yeah, they were pretty cool actually. So that's do you have questions? Yes, sir.
The satellite actually hit the rocket. Yeah.
Yep.
Kind of had it backwards.
Oh, okay. Well, that's a strategy we're taking. They're going to hit us. We're going to hit them first. Yes, sir. Back there.
Are you familiar with the FAA's fidelity standards for aircraft simulators? And have you considered applying your semantic fidelity approach to an actual full-flight simulator in the Air Force's fleet?
So I'm a little familiar with it. Yes, I looked at it. It's been a few years since I looked at it. The specifications that it has, they're not detailed physics. For instance, they would say Model A, Model B, Model C, and Model C 1, 2, 3, whatever. And so it has it's more of a localized specification for how they classify their aircraft and features. But yeah, I looked at actually a wide variety of fidelity strategies across various domains and in the industry. And so, this was the work of doing trying to leverage other strategies that have been used across the board. And yes, certainly open-minded and, willing to bring whatever knowledge is useful to solve this problem. Because if you went to the panelists, the open ceremonies yesterday, and the panelists were talking about we're really relying on digital engineering and MBSE and such, but they don't tell us the complexity that I showed you this morning. There's a lot to be able to make these things talk to each other and be on the same page. That is not a trivial undertaking. Did I address your question? I hope I did.
Somewhat. You said a minute ago that, or my understanding was that the goal here is to have systems engineers who don't have to be subject matter experts to be able to put everything together.
Right.
Given the level
So I didn't mean to imply that you're not going to need understanding of that. You do need to obviously you have to be an engineer and you have to understand the domain. But what you don't have to necessarily be is a subject matter expert. If we provide for instance, if there's ideal rocket equation, okay, if you have a lot of perturbations, that's just an ideal thing, and the ideal equation that you learn in physics in college. But there's a lot of perturbations that you don't get in college, that you only learn in industry. And those perturbations, all that physics, all those relationships there, are the ones that are provided by subject matter experts. But we can provide some of that in a repository so they can be at least aware of that and be able to select it and then have an intelligent conversation with the subject matter experts so you can put models that are somewhat coherent. Bridging the gap, basically, or closing the gap, rather than having a systems engineer that has no experience in the domain to try to attempt to put together models that, without having that insight. That's the idea here. That's another hand. Yes?
So what would you say are the next steps? Because this is really interesting, but if I was to have my head spinning on how to implement it, and where do you think you are in terms of, it seems like it's a relatively new thing. Are you talking to INCOSE or OMG or anyone like that?
Yes, we're talking to, there's a modeling and simulation modernization initiative at the Aerospace Corporation, and they're working with other organizations as well. The next step right now, which is what we're working on, is implementing that phylogenetic taxonomy in MBSE constructs. How can we make it or standardize it in a way that can be useful across the board, so that folks are not creating their own ontologies, or at least that their ontologies fall within that taxonomy, so that everybody's on the same page, so you can work across domains and not have some orphan ontology that is not going to be useful or is going to need a Rosetta Stone to communicate with other ones. That's a big problem right now, that everybody builds their own thing, and then when you try to make them talk to each other, it doesn't. So we need some kind of reference by which everybody is in agreement. The folks at MIT putting together, if you're familiar with BFO, the basic formal ontology, the premise there is that you got to have a high-level ontology, which is really what it's called, a taxonomy, okay, that allows that everything it follows a similar approach. Even if you're dealing with different kinds of physics or different kinds of domains, that you still construct it in the same manner, so that when you get to a point where they do need to communicate, then you have a similar, start trying to communicate this end with the other end, that kind of thing. So we're building that right now.
And we're also,
I'm sorry.
sorry.
Follow?
The Aerospace Corporation?
Yeah, right now it's still exploratory. Yes.
Yes. Yep.
Yes, ma'am.
Hi, Rick. Excellent.
Hi, Simone. Yeah.
Excellent presentation.
Thank you.
I love the underlying concept. I will ask, because I know I'm working on something similar, that yes, you have some fundamental equations like signal to noise ratio, the basic jamming equations and things like that. But the one thing that's unique to individual simulations that drives how they implement those equations is their underlying assumptions.
That's right.
How does that get captured in this? Because you might be using that fundamental equation, but you may have made some assumptions in how you implement it.
Right. So exactly. So now, it depends what you make assumptions. But let's say, let's say a simple example. The one that I use a lot is you do a simple projectile motion. Okay, and that's going to give you X, Y, Z locations. Now, if you add drag, you're going to have a different trajectory. Okay, so you can say the simple projectile motion assumes no perturbations, assumes a certain type of conditions. So those assumptions, are part of the accuracy part of it, part of the measures of quality that you wrote a paper about. So you capture those as part of the accuracy, the fidelity specification. All those fall into the fidelity specification. Will capture all those assumptions. Absolutely. Thank you.
Cool. Thank you.
All right. Thank you.
Yeah, that's really cool.
Hello, everyone. Welcome to the Best Paper Session 1. Our third speaker and presentation is Enhancing the Total Learning Architecture for Experiential Learning by Mr. Mike Hernandez. He is the Director of Business Development at EduWorks and a learning engineer. He brings over a decade of defense experience and has been a contributor to the Total Learning Architecture effort since 2016. Throughout his career, he has stewarded the technical pragmatic development of multiple projects related to the competency-based learning, performance tracking, and data analytics for the U.S. Navy, Army, and Air Force, as well as the OSD. So, ladies and gentlemen, please welcome Mr. Hernandez.
Hi, everyone. So thank you for attending today. Thanks to the committee for this opportunity, and to my co-authors, Dr. Robbie Robson, Fritz Ray, Tim Welch from EduWorks, Dr. Ben Goldberg, our fearless leader at DevCom, Mr. Kevin Owens, the University of Texas at Austin, and Mr. Shelley Blake Plock from Yet Analytics. So people are still trickling in, but I'm going to get going. So why are we here today? So we're seeking better learning outcomes and improvements to investments in training systems through data-driven evidence. So what does that mean? What are we going to go through to get to that idea? We're going to talk about underlying theories, the open source technologies and open standards, and finally some ideas on how other programs can reuse this work to benefit their own training system acquisitions and scale. So how do we get here? So the SteelRR project, Synthetic Training Environment, Experiential Learning for Readiness, is meant to answer some ideas we have around the STE. So we're actually in the middle of a group of learning technology efforts. So since 2010, DevCom has funded the Generalized Intelligent Framework for Tutoring. The ADL initiative has put money into Experience Application Programming Interface and the Total Learning Architecture. And beyond that, many people contribute to standards that are critical of these kind of efforts. We'll be covering how all of this is a part of our project, so that SteelRR is meant to highlight a scalable data strategy for learning data in the U.S. Army STE, and how over the last 2 years, 2020, 21, now we're in year 3, we've established this software architecture. Let's see here. Developed assessment models for synthetic, semi-synthetic, and live training experiences, XAPI profiles, models for proficiency, and all in the aim of supporting U.S. Army squad development and then scaling both horizontally and vertically. So that was a lot of jargon, and there's going to be a lot of jargon in the presentation. I'll do my best to explain it whenever it comes up, and so I was kind of setting myself up for this. But this is a lot of the kind of things that in our community you hear a lot around what we're trying to do to innovate with learning technology. So we'll do the best we can as we go through it. All right, so SteelRR is based on the theory of experiential learning. This means we prioritize exposing learners to the most effective and efficient experience we can provide to meet a learning goal. So the loop you see on the right is reflected in how data flows through the architecture. Goals drive setting what's done in exercises. Data is collected, soldiers work their way through those exercises, we provide feedback, and that's to support leadership and those soldiers to reflect on what happened. The data is then leveraged to pick that next best thing that we can. Now, effectiveness in this is a function of keeping soldiers in the zone of proximal development, which again, jargon for jargon. But it's about hitting the sweet spot of keeping them at the right level of complexity, stress, and ultimately driving skill adoption to reach mastery in the best way that we can with the resources that we have. So let's expand on this a little bit. So early in the project, KO, Ben, and many others started saying, all right, well, what does this look like? This WHO model of how well you perform over time, how hard it was, and how often you do it. What would this look like in a graphic form? I really like this. This is something that I wanted to highlight here from some earlier papers. And so we want to keep people in that right spot, whatever they're doing. And so, when you combine that with one of the things that we believe in our group, which is that, I think this is pretty well accepted, that if you don't practice something often, you start to have skill decay. So, it's when you build many of these systems, you're aiming to fix one thing. You're aiming to teach one skill. But in reality, you have to maintain proficiency across all of their skills. We want to have the best squads we can. We don't want to, focus on something so much they start to lose these other abilities that they're going to need for combat. So at the ADL, I was lucky enough to work with like Dr. Schatz and Brent and Jerry and think about what does this look like in a career, right? So the TLA has a lot of this in its policy around how you use these data. And so we started looking at these control loops. And so, what am I doing today? What do I need to do to get that next credential to move up in rank? What is that going to do, to my career? And as I gather data around that person, how are they going to develop? And, one of the things that we found is that, when you apply the experiential learning approach that we're prioritizing, it doesn't break this, it complements it. So as part of the exercise in writing the paper, we talked as a team about, so we're getting this evidence around experiential learning at all these levels, and that reality is necessary. You're always gonna have to have credentials and MOSs to have people progress through their careers and manage it. Like, you have to do that. But in parallel, you can also start focusing on gathering some data and thinking about, if I hit this evidence and I'm starting to generate these assertions, this might actually help me realize where some issues are forming and how I think I should be doing something. And I think this is seen a lot in training systems acquisition. So we get requirements and you start building something, and then you get to a point where it's into LRIP and you're starting to get it out there. But then T&E's getting in there and they're working with SMEs and seeing how the trainer is reacting, how they're reacting to it and what they think, and you start making adjustments. So this is just a way to digitize kind of what happens anyway in our community. So we've covered the learning theory, talked a little bit about this control loop structure for context. We're thinking about lifelong learning, and so from this point we have to start to kind of dive in a little deeper to get through this project and what we wrote about in the paper. So there's some premises here that there's tons of data coming out of military training. And we think that often it's not getting captured, or if it's getting captured, it's not in an interoperable way. In the preceding paper that was presented, that actually highlight that at an even deeper level, which was a great setup for me. And so we have to think about how are we going to capture that data to do this longitudinal analysis, and what is that going to look like? And in SteelRR, there's a lot of us who are involved with standards at varying levels of being a wonk, and that is reflected in the project, and that's meant to support it being able to transition, get out there and do some good things. So that's sort of how the data structures, we're working on some standards. These are the examples of the core ones in the project. So then there's a spine to the systems, right? So when we build out, the prototype we've been working at, this is what it looks like. And so, like I mentioned earlier, GIFT has existed for quite a while, and it provided some existing tools where we could rapidly start to hook up into some training systems, and there was a lot of selection of existing training experiences for us to leverage. So one of the concepts in here, and the guys from Yet Analytics have helped a lot with this, is we use their open source LRS, and we're going to talk about scaling, but I have to capture data from all these different experiences, and I have to get it to where it needs to be. And we do this through these XAPI profiles, which are this established business logic of where I need to move some data. Beyond that, the competency and skills system samples what's captured, and then we have models and frameworks that represent the knowledge, skills, and abilities, which we've used to link doctrine down to the tasks that we see that we're telling people they need to do to develop the right experience. So that's where the spine of the system. So this is how the current prototype works, and there's a lot here to take in, and we're going to work our way through it. And we want to highlight some of the ways this would support U.S. Army training. So in the U.S. Army, you follow this cycle of plan, prepare, execute, and assess. And so that is a core requirement to how we've implemented the way data flows through the architecture. So starting at 1, we're actually going to start with assess. So we're assuming that we've already collected some data, things are there, people are ready to train. There's a goal set, right? And so we have a dashboard that's built up. And then one of the things we've been working on is a navigator. And this is a kind of like, if you've heard of recommenders, basically it looks at all this evidence, and then the recommender tries to suggest to the NCO or leadership what's the next thing that they should try. From there, that leadership sets the next thing for the person to do. Well, you have to establish what's going to occur in the exercise. And KO's team at University of Texas have been working on an experience design tool, and this is meant to supplement existing exercise design tools, where you can look at it and say, all right, these are the conditions I need, this is the right, things that have to be within a simulation or a live event in order to stimulate the proper, response from the student based on the evidence that we already had. And so a digital artifact comes out of that called this XTSP, and we use that to go to GIFT, which is, GIFT is hooked like a spider web into a bunch of different training systems. And GIFT then tells those training systems what to launch, how it should be set up, and then the soldier moves in and starts doing these exercises. So within that, Gift has had a new capability added during the project where it's able to export XAPI, and that goes to the LRS layers, it's processed through the CAS models, and now we've gone through the full cycle, we're moving on to the next training experience. So you look at this, you're like, that is a really complicated way to build a training system, if I'm building one training system. But it's not. This is actually a two-dimensional representation of an architecture. So the architecture is meant to scale out. So if you look, this is a good example, between 5 and 7, if I'm deploying this across the US Army, I'm gonna have LRSs in disconnected environments capturing stuff at the edge on laptops. I'm gonna have things, at different training centers. I'm gonna have some data coming off of traditional e-learning platforms, and I'm gonna be collecting this where I need to collect it. Now, if you try to move all that over, constrained networks, it's not going to work. It's very similar to the last presentation's discussion about, ensuring that you have proper data flow. What needs to happen here is you have to filter it and send the XAPI you need to the right people in the right place. That's how you use XAPI profiles. Then CASC is present to make sense of that, perform that longitudinal analysis, and you can use those assertions as a way to broker what needs to happen next if you have to send it to an HR system or if you're just going through the next cycle of training. So I hope that helps. All right, so let's take a step back from what we just saw and talk about it again in I think a simpler format. So these are all the kind of data layers that you'll see in this architecture. And what's going on is as I drop in experiences, synthetic, semi-synthetic, and live things into it over time, I'm going to learn things, and things are going to change. This is happening on our project over the last few years. We find better ways to write XDSPs. The XAPI profiles get tuned. We start thinking of different things we want to add in the model. And so as those change, by preserving these data artifacts in the different places where they need to be, you'll start to build a library of things that you can reuse to enhance training in the future. And so if I have all my XAPI and I change my model, okay, I'll just run the XAPI back through it and see if that had any effect. If I think I need to change a skill decay rate, I can do that, run the data back through. And that's sort of the idea behind the way we've set this up. So that was a lot of the things we've been doing on the team, the prototype and things like that, but we've also been doing some data collections over the last few months with our partners at the New Jersey National Guard. We've had an excellent opportunity where they've supported us going into their advanced leadership course, adding synthetic training, building out some enhancements to our own models, and running these soldiers through things. This just ended. There's a lot of data to go through. It's keeping us quite busy. But in our community, it's tough to do these data collections, and it's a lot of work when you do them. And so it was definitely a great opportunity. I'm sure in the near future, Dr. Goldberg, we're going to figure out the best way to share this with the community as well for our results. All right. So I'm a former acquisition guy. I worked in OCTSD for quite a while. And for this to make an impact, we had to really think about, okay, what would it look like in an acquisition environment, and how do you show value from it? Just buying things to buy them is not going to work for most program management offices. So as STEE becomes a reality, we're going to need a comprehensive interoperability standard set to establish that chain of evidence we discussed. So there's an engineering aspect that's different here than when we think of systems engineer and then we think of instructional designer, which you see on a lot of our teams, right? And that's what we see as the practice of learning engineering. And our team and I feel that when you establish that, that's how you start to be able to build out those control loops and bridge that structure within your team to figure things out. And that's how you want to get to that longitudinal analysis capability. One of the exercises we did that was very exciting and was so much fun was we went through all the kind of DIDs that you'll use to buy courseware, to buy a simulator. We started to think about, okay, well, what do these DIDs do now? What kind of data can I buy them? What are the standards they're aligned to? And what would I tune in them to start making adjustments to be able to get the things I want for a Steeler architecture? So you need the spine of things to make it work. It's all open source stuff. And even if you set that up, you still have to be able to work with your partners to get the data sets represented in the things that they code and they build. So this is sort of a sampling of what we looked at through it. It's that flow of, it always goes requirement, design, build, test. And here it's really requirement, put out your competency-based experiential learning package, get all your stuff set up the way you want it for your XDSPs, the XAPI profiles, frameworks, all that. Have your learning engineering cycling through as you're building this and getting it out there. And then you start having to do continuous validation. And that's the one where it gets really interesting, is because on the continuous validation cycle, now you have to have a reason to use the data. You have to be giving it to people who have interest to it. You have to tune where you're sending outcomes so that people from policy all the way down to, you know, tactical training can make it work. You know, and this isn't, it's the same thing as the control loops. We're not trying to replace courseware or break, you know, the nature of what simulators do. It's meant to enhance them through data. So, went a little quicker than I expected, but, you know, in conclusion, you know, we were given this wonderful opportunity to share what we're doing and some of our ideas from the Policy Standards Management Acquisition Group. You know, we hope that we see changes where people start shifting to picking up experiential learning. These standards are pretty mature. We hope this helps you manage life cycle of systems, and thank you for the time.
Floor is now open for questions.
Yes, sir.
Can you go back to your previous slide, please?
Sure.
I'm trying to get a clear sense of how this is being applied. Is this being applied as part of the acquisition sequence of a new capability?
So DevCom's our sponsor. This is a project meant to highlight an opportunity to the STE. Aspects of this have been in the acquisition system for quite a while. The DoD 1322.26 encourages the use of XAPI. Competency-based learning, depend on the service that you work in, has varying levels of adoption. The Air Force, it's highly formalized, but it's making its way into other policies. But this specific approach is not within it's a fully baked acquisition pipeline. This was a thought exercise here. One of the jokes I made too was, wow, this could really trigger a lot of one-time DIDs for somebody, or they could do it right and actually build this out for real sustainability.
I see this as an example. We're looking at this as treating training as a capability in its own right, and how this actually fits into that type of model, where you perceive the training activity as a capability in addition to the capability that you require.
Yeah, very much so. And so, you know, one of the things with this too is it gets back to there's a timing and an adoption cycle that we see a lot with these kind of projects. So if I'm buying something and I get funding and I have to get it out there, you know, there's the accuracy and the concurrency with the system being developed, but there's also this adoption timing, you get the data out of it, right? So like you have to build in, if I'm gonna build XAPI into a system, I need certain things available to catch that data. I need someone who knows how to work with it. And one of the ways that we accelerated it on this project is through GIFT, because GIFT already had a lot of capability. Once it had the XAPI output, that opened up 10 years of connections to things like VBS3 and land nav trainers and all kinds of stuff to be able to help us get through things very quickly in the beginning. So, yeah.
Just to add to that, obviously the passion and the perseverance is there. What was one of your biggest stumbling blocks? And if you had a magic wand, what was the one thing that you would actually fix?
I'm looking at my colleague Ben in case he usually has really good answers for this.
So I'm a co-author on the paper. You know, I think a lot of the challenge in and of itself is stimulating these models with viable data sources to get to a satisfactory training classification. That's what we mean by performance and incompetency. But there's a lot of emphasis on being able to establish these data repositories. And what we really want to emphasize is the critical requirement for context to be captured within those data lakes to support this type of complex performance tracking over time. But we are in complete agreement that we view the training experience itself as a resource within a larger ecosystem opportunity to apply knowledge and skill. But we also want to emphasize deliberate practice, make sure that you're practicing under the right conditions to support that continual skill progression.
Yeah, from a systems engineering, I'll give you the answer I give on any project is it's tough to work with non-accredited, you know, stuff and getting it ready to be able to put into the right places. DevCom has a lot of good structures in place to be able to accelerate the things we had to do to get out there and actually do the data collections. So that was nice here, but that's a challenge that I think that gets in the way of a lot of innovative stuff. So. Yeah. making it easy. All right.